is what we had till today. So we talk about dealing with big data, which means streaming and parallel computation, either a lot of machines or a lot of threads. And for this, we have the merge and reduce tree. And we defined the first definition of Coreset, the very general definition, so we can use the merge and reduce tree and reduce the problem to just reduce a set of 2x point to x point. So we get rid of the big data and we just say how we can, what is the minimum x that we can compress two sets into one, so we can use this framework evolve. And then we show some Coresets for a specific problem, and I try to give you a general solution for the case where cost is just sum of some distance function over the point to a query. This was the cost of the point to a query. And we reduce this problem to computing two things. Dimension of Q and sensitivity. The first one is usually very easy because it's related to problem in computational geometry that people solve for years. And actually, even if you don't know it, for the algorithm, it doesn't really matter. Just tell you how much samples you need to take. And in practice, you can just take, it depends on the memory that you have, even if you don't know the exact analysis. More harder in theory, and also more important in practice, is the sensitivity, because this defines the distribution of the non-uniform sample that you need to take, which point you need to take with high probability, and which point with small probability. And today, I will talk about, give some example how you actually bound this sensitivity, reduce this problem also to approximation, fast approximation algorithms that's related to the original problem that we want to solve. So I will start with a quick example. So suppose that, let's start to construct Coreset for the SVD problem or the vector multiplication. So what we want is a Coreset in the sense that for every x that you give me, and A is an input, we have this property. So the input here is a matrix, n by d, where d usually is much more than n. We have some epsilon, and what we want is a diagonal. We want a sparse diagonal W. So we want to select some rows from A, so the sum for every x, the norm of ax squared and the norm of the weighted rows of A multiplied by x squared will be approximated by the up to epsilon compared to the value that you actually want. So the fact that we want to subset is important. For example, if the input is sparse, so if this is the Wikipedia document term matrix, for example, you want to preserve sparsity, so that's why you want actually, if the rows are sparse, the subset of rows, the weighted subset will also be sparse. But in general, if you don't care about sparsity, there is a very simple solution. Actually, you can have Coresets with no error. So for every x, you'll have this property with equality. When this is n by d, and this is just d by d, which is kind of analog and related to the exact coset that we have to for the one mean problem, for the sum square distance to a point. As explained yesterday, this is a sum square distance to a hyperplane that is orthogonal to x. And someone know how to compute such a matrix C, size d by d, based on A, so that for every x, this and this will be the same, exactly the same. Any guess maybe? Okay, so actually it's very simple. You already learned the tricks. You can use either the QR decomposition. So you can write A equal QR, the Gram-Schmidt that you already learned. So I meant you this, and what you get is AX is QRX. But this is orthogonal matrix. So only need to compute Rx, but R is D by D matrix. A more specific case is to use the SVD. And now if I give you vector x, what you want is u dvt x squared. You can get rid of the u because it's orthogonal. And dvt is a d by d matrix. But in both cases, we get a matrix that is not subset of the input, and we kill the sparsity. Not unlike random projection, this is deterministic matrices, and it always works. There's no probability here. But the framework that we talked yesterday about will take weighted subset of the points. And the question is how to bound the sensitivity that we defined yesterday. So for our problem, the sensitivity is for a point P, which is a row in A, is the inner product of the row. So we want to maximize over all possible x the contribution of the row, which is P in A. So one row multiplied by x squared, you get this value, divided by the total cost, which is this. So for a specific row, what is the query x that is dominate the cost, and we must take it for the Coresets. So in order to bound this, first of all, we will compute the SVD of A. And you observe that for some x, P, so we have a matrix A, and the ith row of A is just the ith row of U multiplied by dvt. So if A equals U dvt, the ith row of A is the ith row of U multiplied by dvt. So this is actually the ith row of U dvt multiplied by x squared. And here we can replace A by the SVD, which is U dvt. Again, use orthogonal, so you can ignore it. And we can just put this is a number, so you can just put it inside. And what we get is ui multiplied by this vector normalized. So this is just a unit vector. And everything squared. Can we bound this term now? So what is this? This is just a unit vector. Whatever x you give me, this will be a unit vector. So we have an inner product of two vectors, and we squared it. So if you have a vector ui, what vector x will maximize the inner product between the two vectors? So inner products, I remember, just the projection. ui, right? The vector himself will maximize the projections on the vector. So we get this is just bounded by ui squared. So it tells us that the probability to choose a point in A for our coset should be with respect to this value. So you compute the SVD and take the norm of the corresponding row in A. How many points we need to take? Well, the total sensitivity is the sum of these sensitivities over all the points. The sum is norm UI squared. But since this is orthogonal matrix, you have here D orthogonal columns. The sum of the squared rows, all the squared entries of U, is just D. So this multiplied by this dimension gives us the number of points that we need to take. Note that it's independent of the number of rows that you have in A, which is N. It just depends on D. So one of the things that people, also professors, that are experts in the field, are quite shocked that they ask me how to compute SVD fast, and you say, oh, that's easy. First of all, compute the SVD, and then sample points according to the SVD. But they ask me how to compute fast SVD, and the first line in the algorithm is compute the SVD. So why does this make sense, you remember? I mean, if the main motivation for using this kind of compression is to compute the SVD fast, why it's okay that the first line in the algorithm is said compute the SVD? This reduction. The input is never a lot of points. We always get about 2D points, compress them to D. We never get the huge amount of data. We apply this algorithm only on small sets. So we want to have SVD for all the data, but we are essentially just running small SVD for very small chunks of data. This we can do very fast. Because when you construct a tree, when you give more and more points, we just need this construction. Get to D, compress to D. Get to D, compress to D. And this is kind of the very new kind of paradigm that you use to in a cluster construction when we actually use existing Heuristic solution just to improve this exactly the same algorithm. So next, let's do the same for a totally different problem, which is the k-mean. And again, thanks to all this framework, we just need to bound the sensitivity of the k-mean or k-median problem. And we'll just take a few lines, and we'll have a Coresets. So again, the implementation of this Coreset is just three lines in MATLAB or Python. Compute the SVD of the matrix and sample point according to the matrix U. Nothing too sophisticated. And then, of course, we plug in the streaming T to handle large data sets. OK, let's move on to the k-mean problem. So in the k-mean problem, we want that for every point, so we sum the point. So Q is a set of k-center in RD. This PQ means the distance of the point P to its closest center in Q. And you want to approximate this by some weighted set where C is a subset of P. I will do this for the k-median problem, but the surprising thing for the k-mean is essentially the same. So the optimization problems are usually quite different. K-median is quite hard and much harder in some sense. For example, the one mean is trivially, but the one median is actually impossible to compute in general coordinate exactly. But for the Coresets compression, it's almost the same algorithm. So I will just solve the k-median, and for the squared version, when you have this squared, just a simple exercise. So we want that this will be epsilon, the original value that we want, to get 1 plus epsilon approximation. So again, the visit dimension is just the visit dimension of k-balls in RD. It's quite simple, and it's an exercise computational geometry, so I won't talk about this, and you can just Google it. Results from the 70s. More harder will be to bound the sensitivity. The sensitivity is the maximum query, maximum over every K centers in RD. This is the contribution of the point, the distance to the nearest center. And this is the sum, the cost for all the point to this query. And we want what is the worst, we want to upper bound for this. Of course, trivial upper bound will be 1, but we want that the sum of sensitivities will be small, something like K maybe, and not N. So for this, to solve this optimization problem, we first use the triangle inequality. So suppose that they give me some Q, how we can bound it. So suppose that we have the optimal solution. Now, even if you have small set, computing the optimal solution for K-mean might be quite hard, say 2 to the epsilon to the K. And we'll get rid of it very soon. But for now, suppose that we just want to proof of existence. So suppose that someone already gave us the K-means and we want to prove that the sum of sensitivity is small. So then you can say the distance from P to your query is dist P to the optimal K-mean, which is independent of Q, divided by the same sum. And if you want to go from P to Q, you go from P to Q star, and then from Q star to Q. So we have this other term, Q star Q divided by same distance. How we can bound this? So this is easy. So we have a point P. The point P goes to the center Qi in the optimal solution. And since Q is the optimal solution, it must be smaller than this value. So what we get is that this is less than same thing divided by sum dist so eventually the next term that we need to bound is the, I'm sorry, this is Q star. So this term is independent of Q now. And here you have the fact that this must be larger than the optimal solution. So the sum to the query is more than the sum to the optimal solution. And now we get a term here that is independent of Q, and we can compute in advance. But this term still depends on Q. So we want to bound it in advance before knowing what is Q. So the main observation, again, we can use the triangle inequality. So we have this Qi star in the optimal solution to the query is less than first go from the optimal solution to P prime. So P prime, we have for every point, we have the projection on the K-mean, the center in the K-mean. So I will, for every point, the center in the K-mean that belongs to P, I will just mark it by P prime. So if you're going from Q star to Q, you're first going from Q star to P prime, and then from P prime to the query. And now we can just sum it over all the points in the ith cluster of the optimal solution. So if we sum each side, we get that this is the number of points in the ith cluster multiplied by this number. And in the other side, we just have a sum of all the points in this cluster this optimal solution go to P prime, the center of the point, and from the center of the point back to the query, to the nearest center in the query. But I have another board. Let's see if I can switch. No, it won't work. No, that's not what I wanted. I'll keep it down here. And this is, no. Okay, we'll just try to finish this equation. So we got up to there, and this is bounded by sum of all the points. So we can just remove this. Because instead of summing just the cluster, we just sum over all the points. And what you get is this is just twice the sum of all the points to this P prime Q. So this is the optimal solution. So it must be less than the sum of distance to the query. And this is the same sum again. So that's why we have twice this sum. And now if we take this equation, this inequality, I'm sorry, and plug it back here, we get the recursive bound. So what we get is the following bound. There will be some nice pictures in a few minutes. So, to conclude, the sensitivity is just bounded by this term, which is independent distance for the point to the optimal solution compared to the sum, the cost of the optimal solution, independent of a specific query Q. And the other term is this, divided by sum, this P prime Q. And if you plug in the last inequality, this sum disappear, and what we get is that this is less than the first term remain here the same, but if we replace the first statement, what we get is this is just 2 over pi. And this is essentially the sensitivity of a point, the boundedness sensitivity of the point, which means that for every point, you should compute the optimal solution for the k-mean and take the distance to the optimal solution compared to the overall solution, plus 2 divided by the size of the cluster in the optimal solution. So if you're in a very small cluster, it will be selected with high probability, or if you're very far from the original cluster, you'll also be selected with high probability. And just a second, what will be the sum? So the sum of this will just be 1 over all the points. You could get sum in two sides. What will be the sum of this? So 2 over the size of the cluster, if you sum over all the points. So that you have pi points on cluster number I, so it will be just 2k, right? This will be the sum of this of all the points will just be k, and we get again total sensitivity that is independent of n. This is the number of points that we need to take, multiply by the visible dimension, which is about dk. Now, note especially that this is independent of d. The dimension just comes for the visible dimension, for the dimension of the queries, and to get rid of this, for example, if we project the points on a small dimensional subspace using PCA, this was a solar paper last year, and we showed that we can run this algorithm on the small dimensional space. So again, we combine techniques. Another observation is that since essentially we need the epsilon over t approximation, in this case t equal k, so we have to essentially use k squared points in the Coresets. Can we get rid of this term? So if you try to bound this inequality, you probably won't be able to get rid of this 2k. But what we can do is just change the problem. So this k comes from this term. Intuitively, this term say if you have small cluster, you must take some points around them. What we did to get rid of this k, this was in the stock paper 2 years ago, is to say, let's solve a different problem. So suppose that you have the k-mean or good approximation. So take the k-mean, put it in the Coreset, and now all you have to approximate is the sum of the point to the query minus the distance of the projection of the point to the optimal solution to the query, because this term you already have. So we just have this simple observation. If you want to compute sum of distances to a query, just take the sum of distance for the original point minus the projection of the optimal solution of the k points, plus this projection again. This thing is just k points. Every point goes to the representative, the optimal solution in the k-means, but we have only k points in the optimal solution. So this is just k-weighted point, whose the sum of weight is n. And all you need is to find the sensitivity of this function, and the sensitivity of this function will be without this, and you have sensitivity of 1. So in other words, we kind of change the problem. Instead of trying to have Coresets for k-mean, we're just trying to solve the Coresets for k-mean after we project the points on low-dimensional space. And we say, OK, let's also point some good guess before we start, and then just approximate the difference between what we want and what we already take, and kind of have few steps as a preprocessing, and we have a new problem with much more sensitivity, where the visible dimension is independent of k, and the sensitivity of the visible dimension independent of d, and the sensitivity is independent of k. So this is generally how we use Coresets. We use a lot of tricks for different approach, and this framework till now it's helped us a lot. It's still an open problem. How, for example, we can compute the first Coreset that I showed you with the k-center, with the maximum distance in this framework. We only know how to deal with sum squared. We hope to get, again, more general framework in the next years. And then another problem that we have is that most of the Coresets depend on some optimal solution. So in the previous Coreset, it was the SVD. Sometimes, if you have huge data, it's still very hard. If you have d point, d squared time for SVD, or d to the 3 might be too much time. Solving k-means, again, it's an NP-hard problem. So the observation is that we don't need the optimal solution. So what we actually need is a very, very rough approximation that we can compute very fast. Before I forgot some acknowledgement, so I stole some of the slides for k-means from our NIPS presentation, and Adira, Cross, and Matthew Faulkner helped me with this. The movie of detecting flying quadrotors with the marker is from a student in Haifa, Suleiman Nasser. And the first application of merge and reduce trees for Coresets by Parent and Matsuda, we generalized this to the parallel case. And the main technique is actually by Sachs for the 17s. But Parent and Matsuda were the first to actually apply it for Coresets. So essentially, we reduce the sensitivity problem to compute some good approximation. And what is a good approximation? So So if you have a set of points, for example, here I assume that you have the optimal solution, which is, for example, the k point that minimizes sum of square distances or sum of distance to the input. You probably heard in computer science about constant factor approximation for a problem, especially for NP-hard problem, if we sometimes achieve, which means you still return k center, but now the cost is at most constant factor compared to the optimal solution. So you're cheating with the cost. The cost is a bit larger than the original cost, but only by a constant factor when you correct 2 approximation, 4 approximation, and so on. Less popular is even more general approximation, which is called the bi-criteria approximation. So not only I give you a few center which constant factor approximation or log n factor approximation to the optimal solution, I also teach in number of center. I use k log n center, for example, instead of k. I still compare the result to opt of k. The opt on the right is for the optimal k center, but I allow you to use more centers, and you can cheat with the cost. This is so rough approximation, so we usually can compute it very fast, and that's what I want to show you now. And actually, I saw this one algorithm, few lines of code that is good both for k mean, k median, and k center, the same result. Again, because we have so many centers there. And the nice thing is that if you look in this proof and you assume that instead of the Q star is optimal solution, you just replace it by this kind of approximation. So the coset size will be only larger by factor of log n. So the sensitivity will be increased by log n instead of 1. So we have coset of size log n multiplied by the dimension, log n k multiplied by the dimension. But you can actually, even if you have this rough approximation, what you can do, and this is again related to the comment that I got in the first day, you can compute coset for epsilon equal 1, use this rough approximation, sample points, and then you have a coset of size k log n, and which give you just constant factor approximation because you use, say, epsilon equal 1. But the coset size will be about k log n for constant d. But now what you can do is to compute an exhaustive set, the optimal solution for this small set, or maybe constant factor approximation, and then compute the coset again using the new approximation. So again, you have first rough approximation. You use it for getting small coset with a constant error. Then you solve again the problem on the coset. Now you have a lot of time because the coset is quite small. And then you have constant factor approximation, and the coset size will be reduced to k. So again, we're moving from a very rough guess to a better guess more and more until we get coset of size k, and then we can run our original heuristic or algorithm. So how this bi-criteria approximation works, it's extremely general. This is the algorithm. So T will be the counter, and F is the output. Just take a random sample. So we don't have any, we cannot use sensitivity because we have no idea where are the important points. So we just take random sample. Now, because we don't have anything better to do for now. But what's the problem with random sample? We miss points that are very far. So instead of just going home, we add this sample to the output, compute the distance for each point to its nearest center in the sample, and we move but only half of the point or quarter of the point that are close to the sample. So if we have outliers there that are very unhappy with our sample, we keep them. We try to approximate them later. We just take the points that are quite happy with our approximation. And we remove them. And we left at the point that they weren't happy with the sample. So we just repeat and sample them again. Add them to the output. Compute distance for each of the original point to this new sample, the point that are left now. You move the closest point and continue recursively. So suppose that there are billions of points here and one point here. What will happen? You sample a few points, will probably be all of them from here, You reduce half of the points, so this cluster will be reduced by half. And this one will stay here. You sample again. Again, you probably sample all the points from here. Half will be reduced. After log n iteration, this cluster will disappear, because every time you cut it by half, and then you will sample finally this point in the end. This kind of multi-resolution approach to getting the far point. And it's not a heuristic. We have a proof. I won't prove it here, but it's quite simple. It's quite general. So for the size, so all you need to sample is about k points in each iteration. And we have k log n iteration because every time we remove constant fraction, so we end up with k log n centers. And the running time is actually O of n, because although you have log n iteration, every time the input you reduce by half. So it's just a geometric sequence. So it's a very, very fast approximation. And you can prove that it's good for k center, k mean, k median. Beautiful proof, but I don't have time to talk about it. A harder problem might be to talk with what do we have lines. So we want to approximate the points by k lines, for example, or a subspace. So we cannot just sample point and return them because the output is a line. So we can generalize this idea. Just take, again, the input. The output will be now a set of lines that approximate the optimal k lines, for example. And the idea will be, again, we'll have log n iterations. Take a random sample. Now the sample size also depends on the dimension of the subspace that you want to approximate, but it's still a very small sample. But now, since we want lines, not point, you take all the lines that pass through the input points through the sample points. So you sample 3 points. You convert them into lines by taking all the pairs of points. Put these lines in the output. Compute distance for each point to the nearest line in this sample. Find the farthest, the closest half. Now it's not balls, it's kind of slabs. Remove them, and continue recursively. Again, we have only log n iteration. We have a bit more lines now, because it's square root of the number of points. Every pair is a new line. But if we want just lines or low-dimensional subspace, it shouldn't be too much. And this is the trick for when you want to approximate points by few low-dimensional subspaces, for example, for topic selection. I have another few minutes. So I show you the practical course that we use for the iDiary project. Back to the problem when we want to approximate points, for example, by k segments. So again, the sensitivity is for each point in general, if you want weighted subspace, is too large, because as we already see, if this is the input points, every point is sensitivity 1, because we have queries like this. For every point, there is a query which is dominate the cost. So SP equal 1, and the sum of SP is n, so we don't have small coset. But the trick was to project the points on the optimal solution for a good approximation. So we first compute the optimal solution. We project the points on the optimal solution, and then, based on the sensitivity, we sample point in proportional to the distance to the projection. So intuitively, if you're very fast for the projection is not a good representative. So we want to select it to the coset with high probability. If we're very close to the projection, since we have the projection, we just select it with very small probability. And the proof for this is, again, based on the same framework, but now the function is at least, instead of distance from a point to a k-segment query, it's the distance from a point minus the distance of its projection on the optimal solution to the same query. And the sensitivity of this function is bounded. So again, we manipulate the input to have a new problem with a smaller sensitivity, and then we can have a small coset that is based on the weighted points plus all the projected points on the input. And again, because of this range function, plus and minus, we have points with positive weights, and the projection is with negative weight. So the algorithm looks like this. We take the points, compute optimal solution with some good approximation, sample point that are very far, take the projection of the point, compare to the sample together with the sample point, and this is the final coset. So for example, if we try to take the dynamic program, the optimal solution on the real data, for about 10,000 points, we get running time of a week. When we run the same solution on the Coreset, which took about a minute, and based on this result for small data, we believe that this is still a good 1 plus epsilon approximation, and the theory support us with this. But the nice thing is that we took a lot of heuristics that we found on the web for solving this problem, and we just ran this heuristic on the Coresets. And this heuristic, again, we're offline, but now we're able to run it for big data framework when we have millions of points and few computers. And the nice thing you see, so in the optimal solution, the red one, you see that the Coreset is always bad, of course, than the original optimal solution. But for some of the heuristic, you see the Coreset is sometimes even better than the result of the existing heuristic, which is kind of nice. And again, we see this phenomenon a lot. The problem that we have with this approach, again, is that just smoothing the signal is not enough because, for example, when I go from home to MIT, we go the same road several times. And what we actually want to identify that over time you're using the same road and same segment. So we want to deal with this phenomena, not only just smoothing the line, but also find repetition of lines over time, which is a much harder problem. So what we did is to observe that usually we don't do just random walk on the planet. I usually go home, walk, taking the kids to the kindergarten, the gas station, the park in the weekend. I visit the same places. Sometimes I go to see some other places, but most of the time it's kind of just hidden Markov model, same places over time. And essentially we have a lot of segments that I'm going to on the time signal which repeat themselves. So we change the problem and we show that we actually want the k-lines that minimize the sum of greatest distance to the points with the following constraint. When you project all the points in three-dimensional space, the signal, on two-dimensional space, to get some kind of a map, you get only few segments. This forces the algorithm to choose k segments so that things will repeat themselves over time, so the projection will be a simple map. This is a much harder problem, but fortunately, this is the same. The candidate set of queries is still k segments. So we can still use the same Coreset and run this very hard problem on the small Coreset using more sophisticated algorithms and heuristic. And again, solve the problem. And instead of getting these maps, when you have a lot of lines that represent the same space, we have the constraint that the projection must be on the two-dimensional space must be few lines, and we get much nicer maps that represent the data. And again, now when we have big data, we can run it on Amazon Cloud and MATLAB and using a lot of computers. This was published in JS with Sang and Daniela Ross. And in practice, in our database, what we have now for the GPS is that the original data is just X, Y, and the time. But on the database, we have the K trajectories based on the M popular point that you usually visited. So for each point, you have the segment, or if the same place, begin point and end point are the same with the letter. And now the trajectory is just a set of letters, which segment you visited in each time. And now we can go, for example, to Google API, Google Maps, and ask for the names of these popular places that I'm going to. So every time that I visit Starbucks, we still recognize that it's Starbucks, and we don't need to ask Google Maps, which have a very limited query time, queries per day. Only for the popular places, we ask Google once, get the text, and add it to our database. I will skip to the open questions because I have only 2 minutes. So we still don't have courses for a lot of famous problems in machine learning. Deep learning, for example, is one of them, neural networks. We have some courses for SVM, but I think we can do much, much better, especially for high-dimensional space. Too few implementations. There are some implementation on the web. I hope to change it in the next year. But we need more practical people that actually test them and evaluate and maybe had more information on how to tune them. What I'm trying to do these days in the University of Haifa is trying to have courses for more practical application. So we start with the system, with the robots or the sensor, the life logging, try to understand what is the right problem that we want to solve, and then have courses that is not based on the problem of the theory people or the people from statistics or machine learning, but actually on a real life problem that we want to solve. And more people that come not from computational geometry and maybe from the practical application that will help us to at least suggest courses would be great. Another very interesting direction is private corsets. In the same context of life logging and sensor, we have one paper about private corsets based on differential privacy with Chaim Kaplan and Kobi Nissim and Amos Fiat. And we were able to prove that unlike in the differential privacy, you're allowed to ask few questions and then you won't give any answer to preserve the privacy of the people. And the answers are also quite noisy with a very sophisticated crypto ways. The nice thing about Coreset is just I give you the private corset once. It's a noisy database, but then you can run infinite number of queries on this small compression without losing more privacy in every query. So this is make much more sense in practice for people who just want to get noisy database and work on it and don't want a machine to ask queries that will stop responding to queries in some point. But unfortunately, we have only Coreset for K-means problem on low-dimensional space, not for subspace, not for SVD, not for high-dimensional space, and a lot of work there. Also, the implementation is a bit tricky. Unlike in non-private courses, we just sample points until we're happy, we don't care about the theory. In private courses, we usually actually want to guarantee the security, not the practical fact that we have good corset. So it's hard to take small samples. We don't have courses for active learners yet, to the best of my knowledge at least. So when you not get the input on the fly. And another problem is that when I give all this kind of strange counterexample, I use strange sets. But in practice, you usually have very specific type of inputs that do not behave like the crazy counterexample in the theoretical papers. And you might want to ask, suppose that I don't want to have corset for every set P in the world, but I have some assumption that it's well clustered, that looks like this. And this assumption might help you to have corset for the case where in general we cannot have corset, maybe for the travel assessment, or maybe for a lot of graph algorithm. If you assume something about the graph or your data, maybe you can have corset that in general for every set of input points or vectors under the sun, we cannot have. That's it, I think. I hope you like it. I really enjoyed these talks, and I'll be glad to hear ideas about a new cursor from you in email or later today. And I have, I think, a few, about 2 hours. If someone still wants to meet with me, I'll be glad to before I leave. Thank you very much.